Buenos días.
Buenos días.
Sí, precisamente quería ver si nos escuchabas. Bueno, buenos días a todos. Entonces, bueno, el día de hoy, today we're going to start the AC3 automatic control session. Well, we have the presentation, so we're planned for from 10:30 to 10:50. So we will start with the first presentation. It's continuous control of time delay system using a hybrid predictor. And the speaker would be Jordi Ferne Contreras. Go ahead, Jordi.
Thank you. Good morning, all of you, and first of all, thank you for being here. I'm Jordi Contreras. I'm a doctoral student at Simvesta, and today's topic is continuous control of time delay systems using a hybrid predictor, which was developed with doctors Bernardino Castillo, Alexander Lokianov, and Stefano Di Gennaro. For today, we have an outline of first an introduction, continuing with a hybrid predictor presentation. Later, we have our control approach using this predictor, and finally, some conclusions about our predictor. Starting with the introduction, we have that time delay systems are also called systems with dead time or differential difference equations. This is a physical phenomena that can be in several control systems like in aircraft, chemical, or communication, where the delay can be in the state or the input control, as my next slide shows, which is, for example, in equation 1, we had a delay in the state. In equation 2, we had a delay in the input, and there is the case on some words where they use or they have delays also on the state as in the control input. For our case, we have the problem of dealing with delays in the input control, which is a problem we requires a predictor because we are going to give to the system and kind of control input like equation 4 to stabilize our closed loop time delay system as equation 5 shows. In literature, there are some predictors like Smith predictor, which basically is a model of the system without the delay and other model with the delay, and these both models are comparing itself, and this comparison is going to feedback to the feedback loop to compensate this delay. Another predators in the state of the art are the integral predator, which is the analytical solution to the linear time delay system. But this predator requires the implementation of a numerical method to solve this integral. Also, the time is maybe the Simpson rule, but it's another predator. And one of the most interesting for our state of the art is the dynamic predator, which is not only predicting, it's also observing the system. That is that they are using only the output of the system to retrieve the full state measurement, and at the same time they are solving the problem of prediction through the Lambert W matrix functional. All of these predictors use continuous in time measurement uh, for the state, for the output, the case. But our case involves the use of digital device, and this introduces a new problem, the use of a discrete dynamics that is giving us less information than a continuous measurement. So for this problem, we have our our system, which is a linear time delay system, where we have a continuous in time physical system and in the state and the dynamics, but there is the output which are going to use in our design, which is sampled. We are a sampling period which is constant. So this operator had three assumptions. The sampling period is known and constant. The pair of the observability matrix exponential A, delta, and C is not singular, and the assumption tree say that the time delay is known and can be expressed as a multiple of the sampling period. So to give us an idea how this operator is working, we had two parts in this operator. The first part is a piecewise continuous dynamics, which is uh, finding what is happening in the intersampling dynamics. Why intersampling? Because in intersampling, when resetting our predicted state, we are set this predicted state xi, t, that is to pretend to be x of t plus tau, and through our reset condition, we are going this feedback to stabilize our prediction error system, which our prediction error is defined in question 8. They are per case in the same, where is a case for continuous, a case for impulse. And this parameter L is our tool to guarantee the stabilization or prediction error system. So the logic or the scheme of these hybrid predictors is basically the feedback from the output, which is sampled, the input, and well, we can sample it or have all the input because we are designing, and the hybrid system logic, which is the reset condition and the sampling instance. And through this flow, we have a predicted C of t. To guarantee our convergence of the predictor, we have in equation 9 the prediction error dynamics, where there is an intersampling error in this differential equation, and there is a sampling instance error. This error is going to be used to extend the prediction error system in Q states according to assumption 3. And from this station of the error, we can build a new discrete mapping of the discrete system in equation 11. This mapping in equation M gives us the parameter L to guarantee that this matrix is sure. Guarantee that this matrix is sure, we have that the prediction error system is going to converge to, or the prediction error system is going to converge to 0. So in theorem 1, we have the assumptions 1, 2, 3 hold, considering our linear time delay system, the hybrid predictor, the extended error system. There exists an L in 12 so that the inequality in 13 satisfies. That is a quadratic Lyapunov function. So the theory 1, if it exists this L, then the hybrid prediction error system solution is globally asymptotically stable. To show the effectiveness of this predictor, I'm going to show just an example from the state of the art of Emilia Freeman, which is a first order system describing a person in the shower. This dynamics was chosen because we can change between two cases, unstable and stable case for systems. Because in the case of the Smith predictor, if the system is unstable, the Smith predictor is not going to converge in the prediction error system. So we had two cases, stable and stable case. And we're going to use an input to compensate the system to avoid that this is going to infinity. So in this slide, in figure 1, we can see two figures, A and B, where are the case of a stable case, and our predictive state is in red, the physical system state is in blue, and through these resets, I hope you can see it, the resets, the predictive steps is converging to this physical system state. And the same case for the unstable case. This unstable case, they are the resets through the impulsive dynamics, and we are converging to the physical system state. So we having our prediction fix hybrid predictor working. Now we are going to to our control approach. How to apply this predictor in time delay physical system? Where basically where to change the state feedback of the variable x or she, because we are going to give this predictive state in order to guarantee that our closed loop system is asymptotically stable. So we have our physical time delay system, the sampling device, and our prediction-based control. So that also our system had to be controllable, like that. That is the pair A and B. Matrix of controllability is not singular. And in theorem 2, first of all, we suppose that theorem 1 holds, and choosing the control inputs as a state feedback changing our variable x for she, that is our predictive state, we are giving a closed loop A plus BKF, which this is going to be asymptotically stable in closed loop. In the same case, there are some simulation examples to prove the effectiveness of this approach. There is this example from the world of Caballero, Osuna, and Luciano, where they are not only predicting, they are observing the system. So we are going to compare with this example from the world then, and also we are giving to us the sampling output. For the case of 10, we are going to give the continuous output, that is the original design of the predictor. And as can be seen in the graph, we have a comparison of the stabilization of states, where we had in blue and red the states stabilized by the dynamic predictor were about 15 seconds, and in yellow and purple the states stabilized by our hybrid predictor, which is about maybe 10 seconds or 7 to 5 seconds. This is an stabilization case. Now we're going to explore other example in simulation, which is the tracking or reference using block control 4, which is this system is in block control 4. We can use this system, and we have sliding modes to us for our control method. So for this case, we are going to change in the reference to not what happened in the behavior. So in the first case, we had a constant reference, and figure 2A show us the reference signal in blue and how our system are reaching without any problem the signal. This can be seen as the case of the stabilization because it's a constant. And in figure 2B, we're using both predictors, hybrid and dynamic predictor, to to show the output error where both operator and are converging to zero. Our operator converging their errors to zero. In the next case, we are changing the reference for a sinusoidal reference, where the reference is in the same case in blue line in the figure 3A is the blue line, and the physical phenomenon is that after those seconds that is delayed is going to happen the output YT. That is the same case that simulation the previous slide, but the new comment for us is that in the output error we have that the hybrid predictor converts to zero without any problem, but in blue dynamic predictor change the solution to ultimately bounded stability. That can be seen in figure 2B. That's our comment for this experiment. Now we have some conclusions about our predictor that well, first of all, this work proposed a hybrid predictor observer which designed for linear time delay system with sampled output. Also, the predictor observer compensates the delay in the input control and provides a continuous time piecewise because we have sampling instance changing the predicted step, and all of this is achieved through our analysis through quadratic Lyapunov function, which under sufficient conditions expressed in terms of persistent reset, the standard prediction error system is globally asymptotically stable. Future work will consider the design of hybrid predictor for non-linear time delay system in non-linear time delay system. And that's all for me. Thank you all for your attention. I am open for your questions.
Okay, thank you very much for your presentation. If you have questions.
Can you show us the Lyapunov quadratic function that you use to prove the stability of the system?
Yes. This is the light or Lyapunov quadratic function, but let me show you. A quadratic function is the prediction error, B prediction error. Can I draw? Let me draw Lyapunov because it's the paper. B, what error? This is the quadratic Lyapunov function. You can see, or it's too small.
Okay, I'm with the idea that you cannot prove stability of a time delay system with a Lyapunov function, unless it's a Lyapunov-Razumiki function. And I mean, that not is that. Also, you can use a functional, but I'm not pretty sure that your stability analysis with that function is really okay.
Yes, I know your doubt because we are no using Lyapunov function to solve the prediction problem. We are using this to prove the stability because the prediction problem is moved from the dynamics that is E C E K minus tau. This is moved to the mapping of this matrix M because we are going to build we're going to give a new discrete system is mapping a new mapping and discrete system. Thus, our measurement state is here, and we're mapping to this state. Maybe it's this is the easy way to understand because the quadratic Lyapunov function is proving that we have asymptotic stability of the prediction error, but no is solving the prediction problem. The prediction problem is solved through the mapping. And let me show you the mapping. This is the mapping that is solving the prediction problem. That is the reason why we are not using, I don't know, a functional like Lyapunov-Krasovsky or another method, because we are moving the problem of prediction to this mapping.
Okay. I would like to see more of that because I mean the detect delay is implicit in the change of the variables. But okay, it seems interesting. Thanks.
Okay, well, thank you. Is there any other questions? Okay, well, we thank you very much, and well, we'll continue with our session. Thank you very much. So the next presentations will be bearing only super twisting control for multiple quadrometer formations. The speaker is Frida Guadalupe Lopez Ruiz.
Hi, good morning, everyone. Let me share the screen.
Okay. Okay, Rob, and can you present it on this screen? So you can't see it here. Okay, thank you very much. Okay, go ahead. We can see your presentation now. Thank you.
I'm sharing the screen. Can you see the presentation?
Yes, we can see it. We can see it. Okay, thank you.
Okay. Good morning, everyone. My name is Frida Lopez from Sinvesta Guadalajara, and today I will present a work titled Bernoulli Super Twisting Control for Multi-Quadrature Formations. This research is in collaboration with Julio Rodriguez, Dr. Javier Ruiz from Sinvestab, and Dr. Héctor Becerra from CIMAT. This presentation is organized as follows. I will start with a brief introduction and the problem formulation, then describe the proposed control strategy and the main theoretical results. After that, I will show the simulation results to validate the performance of the controller. And finally, I will conclude with some observation and future work. In recent years, multi-agent systems have become a very active research field due to their applications in robotics, autonomous vehicles, and unmanned aerial systems. Formation controls allows a group of agents to cooperate to maintain a desired geometric pattern or follow a target. It is crucial for applications like surveillance, mapping, and cooperative missions. Traditionally, formation control has been distance or position-based, which requires each agent to know relative positions or relative distances. However, these measurements are not always available, especially when GPS is unavailable or communication is limited. For that, our challenge and in this work is to design a robust control law based only on bearings. But what is a bearing? In our work, we focus on bearing-only formation tracking. In this slide, I summarize the main ideas from previous works related to bearing-based formation control. First, the bearing rigidity theory provides a theoretical framework formation stability and geometric uniqueness of formations. This theory ensures that a formation can be preserved up to a translation and a scaling factor as long as the bearings among agents remain constant. Then several strategies have been developed for this purpose, such consensus-based, sliding mode control, and proportional derivative controllers. But some of them have some important limitations, like lack of robustness against disturbances, and the use of the simplified leader-follower dynamics. On the right, we can see a geometric representation of these vectors. We have two agents, A and J, and this is the vector of the relative positions. We can see that on the right is that the bearing vector is the normalized version of the relative positions. We have some other elements like the derivative of the relative positions that include the relative velocities. This plot also illustrates how the bearing directions is related to the agent's trajectories, showing that the bearing captures directional information of the agents, but not the distance between them. The derivative, denoted like with this analytic function, describes how the direction of the bearing changes over time, and it can be expressed using the orthogonal projection matrix. This projection matrix removes the component of the motion that lies along the bearing. In other words, it ensures that only rotational changes of the bearing are captured, but not its magnitude. Okay, well, the main contributions of this work is that we propose as robust super twisting sliding mode controller. We approximate quadrature dynamics as perturbed double integrators and guarantee the deformation tracking with no leader motion. And finally, we validate our results in realistic gazebo simulation environment using a swarm of 10 quadratures. At the same time, we compare or propose our controller with a conventional proportional derivative bearing only controller, evaluating the performance in terms of accuracy and disturbance rejection. For that, we define this problem statement. Well, we consider a group of agents with a number of leaders which move with time-varying velocity and a specific number of followers. The objective here is that the leaders move with a time-varying velocity denoted by this variable, and this is unknown to the followers. So the objective for the followers is to achieve a desired position such that the actual position converges to the desired position as time goes to infinity. Formally, the desired target formation is defined by the bearing vectors. So the problem formulations focus on that the current bearings converge to the desired bearings so that the desired formation is achieved. The proposed formation control considers a group of n quadratures. So the dynamics of each quadrature, which are inherently nonlinear and supposed to be perturbed, can be approximated by a double integrator model. This simplification may be obtained through linearization around a hovering equilibrium, including a gravity compensation, where the position and yaw angle behave as a set of independent double models. The followers are modeled like double integrator systems where the position and velocity are the states. The control input to be designed represents the accelerations, and the disturbances such as a wind or model of dynamics are included into the model. To achieve this, we first define the formation errors using the bearing function and the incidence matrix from graph theory. We obtain its derivative and the control input to be designed. For the control design, the proposed super twisting control law considering a linear sliding variable with the bearing error and its derivative. So that this control law introduces two continuous terms, one proportional to the square root of the sliding variable and another integrating its sign. This ensures finite time convergence while avoiding shattering. That is a common problem in conventional sliding mode control. Before presenting the theorem that we use in this work, it's important to state some assumptions. So we assume that disturbances are uniformly bounded, the target formation is infinitesimally very rigid, and each agent is capable to measure the current bearing of its neighbors. And this measurement is typically obtained through onboard sensors such as cameras or optical flow sensors. We also assume that the low-level controller of each agent ensures convergence to zero and no collisions occur between agents. So this assumption allows to focus the analysis on the bearing-based formation control. This theorem presents the main stability of the proposed controller. We start by considering the multi-agent system previously defined, together with the formation error and its derivative. The control law shown in the previous equations, we allow to guarantee the convergence of the errors to converge to zero as time in a finite time. So the systems and the errors, all systems converge to zero as time goes to infinity. In this slide, we describe the interaction topology of the multi-agent systems. The figure on the left illustrates the communication links among the agents within the formation. Each node represents an agent and each represents a bearing measurement or a communication link between two connected agents. The adjacency matrix shown on the right mathematically encodes these connections. The selected gains for each controller are detailed in this table. Okay. We implemented two controllers only for comparison, and the bearing error is shown by this analytic function. It's evaluated by this metric using this equation, and its evolution over time is shown in this figure. The bearing error comparison demonstrates that the super twisting in blue achieves faster convergence and smaller steady-state errors compared to the proportional derivative controller in orange. This is some results of the comparison. And on the right, we can see the trajectories of all agents in three-dimensional space. We can see that the followers successfully follow the motion of the leaders, maintaining the desired formation while tracking the leaders. So The trajectories respect to time of each agent is shown in these graphics. It is in terms of position. In addition, the control inputs of velocity remain continuous and smooth, showing reduced shading. These results are for each coordinate. The experiments were carried out with 10 quadrotors simulated in gazebo, 2 leaders and 8 followers. We use the full dynamics of the quadrotors for the simulations. The first experiment is with the proportional derivative controller. So we can observe some disturbances in the formation due to the disturbances in the system and the motion of the leaders. For this controller, we can observe the performance implemented for these 10 quadrotors. And our second experiment is with the proposed controller using the super twisting algorithm. Is the same trajectory, but all the agents achieve faster formations. These agents only use while the leaders move with time-varying velocities, time-varying trajectories. The followers only use varying measurements, like I described in previous slides. And the followers maintain the desired formation, and we don't know the measurements of position or velocity. In conclusion, we present a robust Bernoulli formation control strategy. We designed and validated a robust control strategy for a group of quadrotors using a continuous sliding mode control law. The proposed super twisting algorithm controller showed better performance compared to the conventional control strategy. That is the proportional derivative controller. And we know the effective evaluation of this control strategy in the formation and tracking of the quadrotors. And for future work, we plan to implement this strategy in real quadrotors using onboard sensors, onboard cameras for bearing estimations, exploring visual base localization and sensor fusion, even the use of computer vision tools. Thank you very much for your attention, and I will be happy to answer any questions.
May I ask? Go ahead.
Yep.
I have a question. You approximate the model of the quadrotor. This approximating model is real. I see is very simplified. So that model, the question number 2, is a good model to design the control.
Yeah, in the literature, we have the full dynamics of a quadrotor, but mostly they simplify or approximate this model by a double integrator model for each variable of the quadrotor. So we have independent double integrator for each coordinate of the quadrotor. We have 3 variables in each coordinate to control the movement in the framework, and the 4th variable is for the yaw angle. Then we have 4 variables, and these are known like flat outputs. So here for the analysis, we use the double integrator model, But for the simulation, we use the full dynamics of each quadrature. Because in the gazebo simulator, we need to use this full dynamics for the purpose of this work.
Another question. What state variables do you have? You have the X, Y, and Z, these coordinates. You have angles, the generalized coordinates. Or in other words, this model or the model is 3 degrees of freedom or 6 degrees of freedom.
Okay, we use 3 degrees of freedom because in the design of the controller, we use some values, some gain values for the super twisting algorithm and the proportional derivative controllers for the 3 axes. So this is our gains. So we consider these variables, but for the control, we consider only the value of the measure of the bearing vector.
Well, we have time for one more question. Miguel Santos, can you turn on your camera and ask your question, please?
Oh, yeah. Thank you. Thank you so much for your nice presentation. I just wanted to ask you if you are using in Gazebo maybe the Rotor S, or you are using the RPilot model for controlling the.
We use the Gazebo simulator, Gazebo Ionic, and ROS rolling.
ROS2. Okay. ROS2. Because maybe it could be useful for you to use the RPilot environment, because there you can model some real sensors like GPSs and or the IMUs, because so that you can have like a better insight of your work using let's say a more realistic simulator or simulation system than just the pure topics that Gazebo yields. So just as a suggestion, maybe you can find it useful to explore that approach.
Okay. Thank you very much. We are working on that for future work.
Okay, good. Thank you.
Okay, well, thank you very much for your questions. So thank you for the presentation. So we will continue our sessions with the next speaker, is Jose Ricardo Rojas Suaste. It's a self-tuning optimal control of time-varying buck converters using the extreme seeking algorithm. Is it going to be the online, or it's going to be it's not here in the room?
Sorry, I think I will present because my student is hoarse. So okay. Yep.
So you'll be making the presentation.
Yes.
Okay,
yes.
go ahead. Okay, go ahead. Thank you.
Okay, just very quickly share my screen. And you slideshow. Okay. Are you able to see my screen?
Yes, we can see it. Okay, go ahead. Thank you very much.
Oh, thank you. Well, thank you very much. We're going to present this self-tuning optimal control for time-varied buck converters. And we have this challenge that sometimes these converters, for example, they are a component of maybe photovoltaic systems or other type of systems where input voltage varies, and also sometimes the load is also varying, so it affects directly the voltage regulation accuracy. Looking at the state of the art, we saw that most of the controllers use line parametric identification, or also direct measurements of the, for example, of the input voltage or the current to estimate the load. Well, these are of course are good options, but they increase the hardware and they are not like optimal. So in our contribution is that we propose a self-tuning state feedback optimal control. It's a very simple algorithm that uses the extreme seeking approach to update in real time the control gains. So first, I will explain very quickly the extreme seeking approach. We have, for example, this general linear time varying system with a state feedback optimal control. We want to always make optimal control to be energy efficient or to constrain some state. And of course, we have an optimal control a cost objective function that should be minimized. And we also, in this case, this type of control is very clever because the key here is to perturb the system to seek for an optimal solution. That's very, I mean, in some in computer science, it's called also like high climbing algorithms. So in this case, we have an approximate cost function, and we are looking for the gradient. So in order to extract the gradient components, we have we multiply that the perturbed cost function again by the same deferred signal, and then just apply a low pass filter, and you have the very quickly the gradient component. So it's a very clever and easy strategy to do it. So this approximated this is the approximated gradient, and then with this gradient we can have also an adaptation law for that the controller can be adaptive. So we found it very interesting, this approach, and we wanted to apply it to this buck converter, where we have the average dynamics, but you probably see that the parameters are time varying. As I told before, that for example the input voltage can be the variations can be due to the for example a photovoltaic panel, in which if there's a cloudy day or the input voltage may vary. And also we consider that the output load resistance is time varying. So we want to design an optimal state feedback control with a feed forward component for reference tracking. And we decided to use the controllable colloquial form for initial tuning, because in this case we will see later that we have some nice properties that we want to exploit. Here, for example, that we see that this matrix is already harvested, so it's very easy if we just start the tuning with unit gains, so that we don't affect the stability of in open loop. And then just we'll compute the feed-forward gain using the optimal gain, the optimal adaptive gain. And also, of course, turning back to the original coordinates, because to implement it in the real model of the buck converter. So now we have we pose this cost function for energy efficiency, and which we give the full priority to a control signal. Then we have the perturbed gain matrix as the extreme seeking control approach state. And then we have, of course, these considerations that are inherent to the physics of the system. For example, that the different frequencies, it's recommendable that most satisfy these conditions. They should be different. Also, we should take into account the Buchenberg frequency, the resonance frequency that should be lower than the different signals, and of course, everything lower than the switching period. Also, we have to take into account the low pass filter curve frequency. Well, and maybe it seems that there are a lot of parameters to tune, but it's not so difficult, and so it's worth just making these considerations. And also another important thing is that the amplitudes must not change the gain signs, because then we lose that this Hurwitz property if this happens. So we propose ourselves timing optimal control that is given in these equations with the according adaptation law, and this adaptation gain matrix must fulfill this condition that basically should adapt faster than the parameter variation velocity. So we can make some assumptions that are not let's say that are reasonable. For example, this the bearing parameters of A and B are always positive, and that's almost always true because the resistance is positive. Also, the input voltage is usually are positive sources. Also, for example, that the bearing parameter change lower than the adaptation law. That is like also straightforward because we have the Bloch dynamics, and also we have the input voltage that is varying very slowly. Imagine, for example, a cloudy day with the clouds are like rather slower than the Bloch dynamics, so it's reasonable. Also, the initial feedback gain is unit gain, and it's always negative because we told that the amplitude of the disturbing signals are according to don't change the sign of the gains. Also, that the desired input voltage is positive and constant, and that there exists the positive constant. Satisfying this also that varies slower than the parameters. So we propose some stability sketch considering those assumptions, and since it's a time-varying system, we consider that can be frozen time asymptotic attractive equilibrium, the voltage reference. So we have this closed loop dynamics and the proof, and you can see it better in the paper if you want. And with a frozen time equilibrium point, and we propose an error, and the derivative of this error is this equation that is a set of stable differential equations. So this matrix in closed loop is Hurwitz because of what we saw before, the assumptions and the properties. So there exists some P matrices to satisfy this Lyapunov equation, proposing a simple standard Lyapunov function whose time derivative is as follows. So the only constraint is that if the velocity or the bound of the velocity is less than the time than this Q, then we can have a negative definite function, so guaranteeing stability. So the other proposition is for the convergence to a bounded value of the optimal equilibrium of the adaptive gains. Again, we consider that let's say the optimality error for abusing of the language, and the gradient expression is this one. Since by definition of the optimum, this gradient error is zero, then we can have just this very similar to the Hessian times the matrix, and the Hessian is by itself is positive because we are seeking for a minimum. So Also, we have this kind of definite function, and when we have the derivative, we see that we have this uniformly attract to the ball centering 0 given by this set. So it's also depending on the velocity of the adaptation, and it's just a matter of tuning. So we only simulated the system because my student is in Mexico and I'm in Italy, so we don't have too much time to do this. But we will do some experiments later. So we used Python and other int functions to simulate, and with these parameters, and we have these nice results. Like, for example, the closed loop dynamics, we have a very accurate system. We can see also that the gains adaptation, or that the gains are moving, are seeking the optimal. But also another interesting finding that we saw is that this extreme seeking, when we apply the same to the same system, the linear quadratic regulator, when we don't have a time varying system but constant parameters, they are virtually the same controller. It's the same response, and it's very nice because this for us gives an insight that we are going like in a right direction. And on the other hand, when we vary the parameters, for example, here we are varying the input voltage and also the load, and we see that then the LQR is completely unable to track the reference, in contrast to our external seeking that is always adapting and is always tracking the reference. So when these are our conclusions, that we presented some external seeking control, and that this demonstrated that is capable to provide state error. Also, that a very interesting thing is that the performance is almost the same as the same basically as LQR. And regarding linear time invariant approach, both when varying the parameters and of course the external seeking overcomes the LQR. And as I told before, our further work is to include some hardware implementation, also to add some noise for other disturbances, to have a further insight of this control approach. That we see that these are promising results. So let's just we will just move to experiments. Okay, thank you for your attention, and I also would appreciate a lot your feedback.
Thank you very much for your presentation. We'd like to ask questions. I would have one question. So this is a gradient estimation type method.
Yeah.
Yeah, because you make a perturbation on the adaptation. I didn't quite. How do you estimate that the gradient? Where is this estimation done? I didn't quite. You make a perturbation, but how is the mechanism or like the main idea?
The main idea is this. For example, that we have this. Back very quickly. Here is. I mean, this is a very nice approach, because we don't need like the actual, for example, a closed form or numerical approximation of the gradient, but instead we just perturb the system, and then we multiply again this the gradient components again times the same error signal. So basically, when we the paper have it clearer, and that when you see the Taylor expansion, then you see that if you filter all the high frequency components, then you only have this part, the estimation of this only of the partial derivative of the cost function. But the idea is that like adding some high frequency, then and filtering, then we only have a rough estimation of the cost function gradient components.
And how critical is that frequency? Like, well, you're using simulation, but when you make the real implementation, would that frequency be very easy or difficult to choose?
Here in the explain this part, for example, that well, this the first one, that the frequencies, these conditions are like must hold for every system, not only for the buck converters, but for any kind of system. However, here in the open loop frequency of the buck converter is important because we need those filter signals to be larger in frequency, but at the same time lower than the switching frequency of the switching period, the PWM signal. So you have like a nice bandwidth to choose theater signals, and of course take into account that you will multiply them again the frequency will become higher. So yes, but yes, with this implication is very straightforward to apply it.
Okay, thank you very much. Is there other questions? Okay, well, we thank you very much for your presentation, and we will continue with our session. Thank you very much.
Oh, thanks to you.
So the next presentation would be by Bernardo Sandoval. So this is Code-of-Sirens design, backstepping control, and saturation-based PD control for the trajectory tracking of the fog. Thank you very much.
Thank you to be Thank you to be here. This presentation is talking about a control strategy design based on backstepping for the depth tracking control of hybrid autonomous underwater glider. This presentation is divided in 5 sections. First, an introduction of what is the vehicle, how it works. The second one is the mathematic model, control design based on backstepping, and the simulation results and the conclusion. Right. These vehicles are unmanned submarines for high-risk application or repetitive tasks for humans. The first one is the remotely operated vehicle. Inside of the vehicle, there is not a human, but this vehicle is controlled by the human on a ship by the cable. Other vehicles, like second picture, is an autonomous underwater vehicle. Autonomous because this vehicle does not need the human control. This vehicle is a glider. This glider is used to monitoring underwater environment. This is the typical trajectory of the glider. And then why is this vehicle interesting? This vehicle and the point of view of the automatic control, this is an actuator vehicle because specifically the Ventus prototype in the picture. It has three actuators: a propeller and at the back of the vehicle to impulse the vehicle forward. The ballast is the ballast to change the mass, and a mobile mass actuator. All this part is go back and forth to change the center of gravity. Then that mobile mass actuator is the only actuator that I use to control. The ballast and the propeller are constant. And also this vehicle is a low cost energy vehicle. Then these vehicles can cover more distance than other traditional vehicles. The vehicle has 6 months autonomy, maybe have more autonomy time. And the application of this vehicle is to monitoring the physical chemical variables on the underwater environment. And the purpose statement, this vehicle is a nonlinear system with a complex dynamic. The hydrodynamic parameters are not easy to estimate. Then we'll have parametric uncertainties. And the system is subject to external disturbances like waves, currents, an obstacle, change of the pressure or temperature. So this is the purpose statement. The objective of this work is design a robust control for the depth tracking problem for this vehicle, the Ventus prototype. And the particular objectives is the stability analysis of the cascade PD control, the design and stability analysis of the saturation-based PD control, and then for compare the results, design a backstepping control and do the stability analysis. This is the particular objectives. Then the contributions of this work is on the topic of the depth tracking control for a hybrid glider. First one, and the closed loop stability analysis of the cascade PD control. The analysis of a saturator PD control and design the cascade saturator PD control, and its simulation to validate the design. All of this is the contribution of the stability analysis of cascade systems. And now the mathematical model, first it is a diagram of the vehicle. It is on the plane X, T, and then the degrees of freedom that we are interested is in the forward motion, that is X axis, forward motion, depth motion, and pitch motion is this one. And then the control on the input control, it was be xj is the characterization of the distance or the position of the center of gravity. Moving the mobile mass change this value of xg. Tau u is constant, is the thruster force, and we have two frames. The body fixed frame is this one, and the inertial frame, the center OY. The typical the general model of 6 degrees of freedom for an underwater vehicle is this one, is presented by Posen. We have a kinematic model, the dynamic model, and the states are the velocity on the body fixed frame. U is the forward velocity, W is the depth velocity, and Q are the pitch angle velocity. and their positions given by the vector eta. The degrees of freedom that we're interested in on x, z, and theta. Then the dynamical model is it has this form. The matrix it has an inertia matrix. It has symmetric matrix and definite positive matrix. The Coriolis matrix, a damping matrix, the gravity vector, and the control input, all in 6 degrees of freedom. It seems as a robot model because we have the dynamic of the rigid body, but it's another war vehicle. It has hydrodynamic effects. The hydrodynamic effects is shown by the damping matrix and the added mass added and Coriolis added matrices. This one and this one. So we have some assumptions to reduce the model. First one, I told you that the model is in 3 degrees of freedom, not 6. The degrees of freedom that are interested is x, z, and theta. Then can we neglect the other degrees of freedom? The angle, the roll angle and yaw angle are stable by the wings of the vehicle. The vehicle is the motion of the vehicle is in low speed. Then the matrix the Coriolis matrix can be neglected, and added mass matrix is diagonal. Also, the damping matrix is diagonal by the low speed assumption. And the balance is calibrated to have neutral buoyancy. Then to reduce this to 6 degrees of freedom to 3 degrees of freedom, we take the rows and columns that the degrees of freedom that we want to use and neglected the others. Then this is the inertia matrix, the inertia matrix, and the same procedure. I do the same procedure with with other matrices. The transformation matrix and the kinematic model, the damping matrix, so diagonal, and the gravity vector. This is the thruster vector, the forces. Tau u is the propeller force. But we need the model on the inertial frame to design control. So this is the inertia, this is the dynamic model on 3 degrees of freedom, and that transformation with that transformation from the kinematic model. Then another assumption is for deep trajectory tracking. Only for the deep trajectory tracking is possible to reduce the model to 2 degrees of freedom because the propeller is calibrated to be constant. Some dynamics can be decoupled. Then the model is that equation, and those equations are a cascade system. So the control design. For the philosophy of this control design, for the control objective, let the desired depth trajectory and the depth position of the vehicle. We come to the control objective is that the error, the tracking error, converts to 0. Converts asymptotically to 0. Then the philosophy of this control strategy is take the cascade system and design controls for each subsystem. The first, the couplet. So I suppose that I know the desired trajectory to theta. It is not real, but I suppose that I can. Then we use this this theta as a virtual control law. It is an idea of backstepping. Then it converts in a virtual control. Theta is a measurable state. Then we have this the tracking error. This is the interconnection of the cascade system. Then and the stability analysis, or an idea of the stability analysis, is given by this theorem. It is the saturated PD control. First one, this equation is the virtual control. It has some feed-forward terms, and this is the PD, the saturated PD control. Then the depth tracking error converges asymptotically to 0. The idea of the analysis is first take the first subsystem, stabilize that subsystem, and prove stability with that Lyapunov function to give asymptotic stability. Then we have the second controller, and its Lyapunov function is the same structure as the first one, but with its variables. Then the stability function of all system is given by the first Lyapunov plus the second Lyapunov function. Computing its derivative, we have this their derivatives, and its terms is backstepping terms. It is the consequence to take a state variable as a virtual control law. Then the other controls that I show is the backstepping, the backstepping control, the PD and the saturated PD. And the saturated PD control is special because I use this function. It's a saturation function. And given by that equation, this saturation function has a characteristic. We can change the function to make it smooth. Then the simulation results, I plan 3 scenarios. The nominal case is free free from disturbance and uncertainties. The second case is disturbance and the center of gravity. It displays 1 centimeter on the mobile mass. And the third case is the parametric uncertainties on buoyancy and inertia to change changing the mass. Then the graphics, we have the 3 controllers. This is the reference, and the 3 controllers are practically the same performance. This one is the PD control, the magenta one. The orange one is the saturated PD control, and the blue line is backstepping control. Is the virtual control, the virtual control. And the input control and the nominal case is the how millimeters the displacement of the mobile mass. Then it is and that are the gains. Those are the gains of the saturated PD. It is an interesting case on the disturbance on XG. And here introduce the disturbance, and it has we have this distance, this error in the depth trajectory at the pitch tree, and the virtual control law has the same behavior because the introduction of the disturbance in the control compensates the presence of the disturbance. That are the gains. By the way, it is not activated because the error is not enough highly to watch a change on that gains. In the 3 scenario, we have more disturbance here. It is the parametric uncertainty. In that, the best performance has the PD, the saturated PD is the line, the orange line. Then the virtual control also has more error here, but it is a good performance also. The input control here and the presence of the disturbances has this oscillation. And now this is the gains of the saturated PD control. When the disturbance, when the uncertainties appear, the 4 gains has changing to compensate the presence of the disturbance. Then the conclusion is that the saturated PD control works as robust control because compensates in simulation results, compensates the presence of disturbances and uncertainties. And also we can design a cascade control, control for cascade system based on backstepping, on a backstepping method. So, well, for time, by the way, thank you for attention.
So we would have a question for one question. One question. Okay,
Yes.
Bernardo, it is known that the connection, the cascade connection for stable system is stable. Why do you need this back step?
Well, the backstepping occurs in the
Do you agree with me? I have two stable systems and I connect them in cascade connection. The result is stable.
Here. Well, first we have to watch the stability characteristic. If that if this subsystem is asymptotically stable, and this one as input state stable, maybe the interconnection of the of that subsystem is stable, is asymptotically stable without the presence of disturbances. The backstepping idea is to interconnect it using a virtual control, using that state variable as a virtual control. Then we have the error of the real variable and the virtual control to get this interconnection of the cascade. This interconnection of the cascade system.
Okay, well, thank you very much for the presentation and the question. So finally, we will begin our next presentation by Juan Abdiel Mercado Velasquez. If you can turn on your camera, please. It's decentralized neural control for individual trajectory tracking in lower limb joints of a bipedal robot. Can you turn on your mic? We don't hear you.
Yes, of course. Do you listen to me?
Yes, we can hear you.
Okay.
Thank you very much. Go ahead with
I'm
the
going to-
presentation.
Okay, yes, and we'll share my screen. Okay. Okay. You already see it, right?
Yes, we can see it. Thank you very much.
Okay. Thank you. Thank you for your confirmation. And thank you everyone for being here, for your time. This work is called Decentralized Neural Control for Individual Trajectory Tracking in Lower Limb Joints of a Bipedal Robot. This work is made by me. I am Juan Abdiel Mercado Velasquez, and also my PhD doctor, Diego Mercado Rebel, from Simvestab. We are two from Simvestab Guadalajara. and also with the collaboration with the PhD doctor, Hector M. Becerra from CIMAD, Guanajuato. So a little bit of overview of this work. I will start talk about a little bit of introduction for this topic, then a little mathematical preliminary so we can understand everything we are trying to show in this case. Then I will show you the methodology we follow to make this work. The simulation and experimental setup we do for validate or theory, and the last the results and conclusion and future work. So as an introduction, in the modern world, there is robots are deployed across diverse domains to perform a wide range of tasks. And a lot of companies right now are using this. Not only are able to use like automatization for develop some tasks, they are using robots, and they want even more complex and intelligent robots that you can do things by themselves. So in these cases, this motivates us to see in this direction of the robots and the use of the control schemes to accomplish some task. And because of this kind of complex systems, there are robots, and in this case, what we are focused on is the human robots. Obtaining this model is sometimes difficult or is a challenge to get or work with this model. And also with the use of neural networks has emerged as a power technology of methodology for the system identification. Okay, now I want to do like a point in this. Our work is not only focuses or main focus is not like human robots. It's a theory that we can use control and technical control that is not difficult, that is easy to implement in the reality and also develop in the mathematics. So there is in the use of these neural networks as identifier and then apply a controller. Some of the previous work that has been do it and is well studied is from the group of Almalanis, the PhD Dr. Almalanis, and 2017, the decentralized control application. We then use this case the shrimp rib like robot that they use network for identification and the use of optimal control inverse for the following of trajectories, and also the group of PhD Dr. Michael A. in 2016 for this decentralized neural inverse optimal control applied to this mobile robot, so they can put some brakes from one state of velocity to 0. So what is our motivation in this? Is the use of decentralized control that allows us to make some systems that work together for solve a bigger problem that maybe can be more challenged to be solved as a union. And also the use of neural networks as identification for this system. Okay, these two systems are make decisions only based on the local information that they have. Is also like a good another benefit of this kind of technique, and the use of the extended common filter as a way of training these neural networks. The problem statement that we make is the performance reference tracking for each joint using neural networks, enabling adaptation to the dynamic change in their state, so the robot's legs can follow a trajectory. A little bit of a mathematical preliminaries. First of all, and the main that we want to talk about is the recurrent high order neural networks. The general equation is shown on the screen, and where x is the state of the neural at the same time k plus 1. The u is the input vector, w is the adaptive synaptic weights, and also the phi state is a vector of nonlinear basis functions constructed from system states and inputs. Inside of there is a number of high-order connection and also a collection of non-ordered subsets of n state dimension. And we can find there also the activation function that we are using for. So to ensure the tracking of a signal that we've been following, we define this tracking error as shown in the picture, where W asterisk is constant. Depending on the application, we can use different kinds of connection. One of them is a parallel that just only use previous predicted states as an input. Series parallel that we will going to use in this work uses measured state from the plant, and the feed forward that use only correct input. In the figure, we can see a general overview of this neural network connection. As I said, the common filter we're going to use this going to enable us to real-time system identification. So we are using this custom common filter for updating the weight is estimated online. So DCF key approximates the optimal weight by linearizing the nonlinear neural network model around the current state. And each step of the time k, this equation that are being computed is the first one is the Kalman gain, where k is the Kalman gain, p is the estimation error covariance, h is the Jacobian matrix of network outputs with respect to the weights, and r is the measurement noise covariance. Then the next equation is the weight update, where w is the vector of neural networks weights at the time k, is the common gain, and x is the measured system output, and x hat is the network prediction of the system output. And for the last, the covariance update is the equation that appears on the tier, and where the only variable that is still not mentioned is the e, that is identity matrix. With this approach, we ensure that the run can convert the fast enough so we can apply and control to the subsystem, and it will show follow the tracking desired signal that we want. So in this approach, we use the inverse optimal control. Why? Because instead of in the optimal control, you have to solve the HGB equation, the Hamilton-Jacobi-Bellman equation. But instead of using that, we will propose a solution to that equation, and we will prove that this equation can solve the cost function that is appearing on the screen. The Lyapunov function that we are using is like it's appearing on the screen, where R is a weighting matrix, and UV is the candidate Lyapunov function that has the quadratic form. All of this has been proven, all the stability, by the group of research of the PhD Dr. Edgar Sanchez. So we are taking this into account. Now the methodology that we've been using. In this robot that we are using, each leg has 12 actuating joints that is treated as independent nonlinear subsystems. And the goal is that these joints can follow a trajectory that we are going to give it. So given these discrete time dynamics are modeled as each one of these motor as this model, and we use the parallel series round model connection. So we define, like in this case, where W is the adaptive weight trained online, and C is the difference of the model, and for the last, C is a linear or nonlinear basis function vector based on the current states and input. This condition ensures that we can track a trajectory, but also we define this error as appears in the screen, where X is the system that we want to follow, minus the T. The T is the state measured by our sensor, that is a real state. And these two conditions ensure that the run correctly identified the dynamic. The other condition is the tracking that we decide to follow minus the state that is measured by the run or estimated. The online weight adaptation, the network weights are updated only online using the external common filter. In each stage of this step, the common filter is updated, the common gain, the weight matrix, and the P, the covariance matrix is also updated in each step of iteration, and it's using the information that has from the earlier stage of the weight, and also to calculate the next step of iteration. In this case, in the case of the weight matrix, we have a learning rate of the neural network that appear in this case, and E is the prediction error that we have that results from the chi minus x, that is the predicted state from the ROM. P is the weight covariance, and Q and R are process and measurement noise covariance. This P and Q, this matrix Q and R has to be definite positive matrix. So the filter is initialized with diagonal matrix P, Q, and R, and are chosen empirically for conversion stability. There is, in this case, we don't use like another way to estimate these values. We start with a starting guessing value, and then in each iteration, we are seeing that these values are changing in order to, with the equation that we have, that is on our online behavior. And then for the control optimized inverse, as we say, we define an error that is C for each trajectory of each joint. And this error is defined as appears in the screen. And we use a virtual input control so we can be sure that this dynamic will be followed in each dynamic of the system that we're using. And then we use the leopard function that we suggest. And with this, the resulting controller that minimizes the quadraticals that we talked earlier is this U, that is the U controller optimized. And we use this U. Once all the system error is defined, we use this U controller optimized for the tracking of the reference. Okay, the simulation experimental result. In each ROM model, use a single layer of architecture with no hidden layers. The activation function that we use is hyperbolic tangents, and this equation that I'm going to show you is a first order ROM, so we don't use the benefit of a high order because the first order was enough to follow the dynamic of the robot and each joint. And also, in summary, each joint operates the following decentralized feedback loop that is shown in the figure. Measure the joint state via encoders, predict next state using the ROM model. Then we update the weights of online via the extended filter command using the prediction error. And then we compute the control input using the inverse optimal control based on the ROM prediction. In this case, we use a robot that is called ROOM3, developed by Robotics. We use the environment simulation gazebo that has physics-based dynamics and has some dynamics in count like gravity, friction, and sensor noise. This kind of dynamics provide us more realistic simulation conditions, in this case for these robots. And all this is running on ROS1 environment. Okay, in this world, each joint is modeled as a decoupled nonlinear subsystem described by these equations, okay, where F and G are the captures the intrinsic dynamics of the subsystem of the joints, and G maps the inputs to the state's evolution, and the gamma sign that is appears in there can capture the couples that is happening between each joint, the interaction that is happening between each of the joints that you have. So the running parallel series configuration is using in this. That is for the first state, weight multiply by the function activation function that we have, in the state one. In this case, state one is position, and the state two is velocity. Okay, inverse optimal control strategy. In each joint track as a desired position, we define and this as an error system as a state, estimated state minus the desired. In this case, we assume that the ROM has already converted fast enough, so we can take the sum that each time of step of the identification of the neural network that is identified the system is also the same, has the same value of my system in that time of k. So in this case, we define two error system, one for the position, another one for the velocity. So we have these two subsystem error, and we stabilize this dynamics by a pseudo control law that this will give you the sure that we can force the state to follow the predict and the value that we want to use. So we can define this C, this we pseudo control with the dynamics as the next step. So we use the error as the next step as the value of our neural network minus the desire of our reference in one step ahead is equal to k multiplied by C1, that is the error, the position error. So with the gain of k minus 1 to can ensure the stability in this case, this leads to the desired velocity of x to desire of this form. And with this form, we can ensure that the first dynamic, that is position, follow the value that we want to use through the second state, that is velocity. But when we get to the second state, we take one step ahead, and that is where appears the U. And instead of using a slider manifold or another technique of control, we use the inverse optimal control, and we use this proposed optimal U as 1/2 multiplied by R plus 1/2 of G transpose by P by G. And in this case, as I mentioned, the P is a matrix of covariance, and it's a matrix that is defined and symmetric definite. That is this value of P and R. They give us the parameters to know the velocity of convergence of the controller. For the simulation, the runs weight hardware initialized randomly, while the EF key are were tuned empirically. The controller was evaluated, and the joints 3, 4, and 5. The joints 1, 2, and 6 are constant 0, so we don't show it, and we don't have to put it here. So the joint 3, we put this table matrix, and we can see that the root mean square error of the identifier from the run is 0.0 radians, so it's little, is something that is well, is this in a desirable factor of design that we want to this value that is the most it has to be 0, but never going to be 0 because the way it is training online always. But in this case, we can assure that the run is following the state, and we can assume that the dynamic of the neural network is the same as the system. So we can put a controller in the run and the system, and it should have the same behavior. This is for the case on the joint 4, and this is for the case on the joint 5. As we see, the trajectory is following, even when it has this like a little noise of high frequency value because the sensors from the robot are not filtered. We can put a filter in there to minimize this, but even with that, the ROOM is able to follow the trajectory. Okay, conclusion and future work. With this, we can assume that the platform that we have, it has already given us a good method of validation of the results. The lightweight configuration of this drone is something that we want to, so we can make a good reference trackings with a light configuration, and these potential model-free neural-based control strategies function with tracking desire. So this is an important point. However, the present study focuses only on individual joint level trajectory. We want to make sure that this take a huge important thing that in this conclusion has. We don't want to aim to outperform the model that is already being known in the in human robotics, that is MPC or PID. We try to demonstrate that with a model-free, even we don't have the model of the system, we can identify and then use this model that we get from the neural network as our model and show the performance with those model requirements. And for the future work, we are trying to improve the inter-joint coordination, coupling terms with explicitly incorporated into the ROOM architecture. We try to use the knowledge that we have from the system and try to deployment on the physical hardware, and also compare it with this model predictive control and PhD schemes, so we can get a more accurate estimate of what is the performance we have, and use it with hybrid control schemes. And thank you for your time.
Well, thank you very much for your presentation. I don't know if you have a question. I would have a question if this means this type of decentralized approach, I could have in a real implementation, small local controllers. What would you need to communicate them between the controllers?
Well, you can do that. You can use that, but it's not necessary because the controllers are just fitted with local information, and that's it. But if you want to, as I say in the future work, you can use like a hybrid combination when you can use these little subsystems run and complement with maybe a model that take into account another variable that are measured outside of these local joint, and it can be more benefit for the neural network. So for a quicker and faster conversion and that kind of behavior.
Okay. Well, I think if there are no questions, we will thank you very much for your presentation. And with this last presentation, we will end this session. Well, thank you very much for being here, and thank you everybody. Oh, there's one more question, I think. Owen? I don't know.
Yes, but do we still have time or not?
Yeah, yes, go ahead.
Yeah, I was very quickly. Just that I see your. First of all, thank you for your presentation. I saw your root mean squared error. That is quite big.
Mm.
It's almost 4 degrees. I know and for bipedal robots, and despite you are only making like crouches or squats, it can be. I think you need to also consider whether this big error is taking or not the robot to the zero moment point outside of the support polygon. Just check that because the error is quite big, and if it's a big size, it's very likely to move out the zero moment point away from the support polygon. Just a quick recommendation.
Yes, thank you. Thank you very much. We take that into consideration.
Okay, well, then we'll this, now we will close the session. Thank you, everybody, and well, have a good day to everybody. Thanks. Presentaciones.